Good morning, everyone. Thanks for the kind introduction. I almost decided to wear my tropical shirts, which I enjoy wearing, and sandals. I refrained today, but the weather has been crazy in Canada and the United States. We're breaking records. I believe the United States has over 2,000 weather records broken so far this year. Most of them have been in the last few days. Chicago has been breaking records for 5 or 6 days straight with temperatures above 80 Fahrenheit. We have places in Ontario that were mid-20s Celsius, breaking records by 10 degrees Celsius or more. Many of the records, though, may only be 2 years old because there was a big heat wave in 2010. But other records go back to the 40s as you go farther west in Winnipeg and places like that. Well, I'm going to give you a broad overview, just like Paul said, and then during the course of the day, we're going to hear a lot more details about some of the aspects. So I'm talking about future Canadian fire regimes and a changing climate. A lot of this work has been aided and embedded by Bill DeGroot, Alan Canton, Alison Newberry, and Mike Watton, mostly with the Canadian Forest Service, the University of Toronto, and the University of Alberta. And this is the first picture of many that you'll see of Slave Lake. There were about 400 structures that were lost, $700 million. Okay, so just checking out the equipment. So I'm going to talk about fire, and I'm going to talk about climate change, and then impacts of climate change on fire activity, and briefly talk about options, which will be a lead into some of the other talks. This is a MODIS picture from May 15th, and this is Lake Athabasca. It's still ice covered. It's hard to see that Slave Lake. And the fire that causes all the damage, you can't see hardly anything from it yet. This is just before the fire erupted. But as you can see, these are smoke plumes. There's lots of fire activity going on this day. Winds were gusting near 100 kilometers per hour, depending on which weather report you want to use. So to understand what may be in the future, you have to look in the past and see what's happening currently. So we have area burn statistics going back to about 1919. We have less confidence as you go back farther in time. And many of these numbers in the top left-hand corner, they were probably higher during the 30s and 40s. So you almost get like a U shape in area burn. And this is very similar to the United States as well, that U shape. So a lot of fire earlier in the 20th century, then a quiet period, and then picking up. We average about 8,000 fires, burn about 2 million hectares, about half the size of Nova Scotia. So a significant chunk of real estate. The running average was about 1 million hectares in the early 70s. So we've already seen a doubling of area burned. And I would attribute this to climate change. Others may have different opinions. These are primarily crown fires in the boreal forest in Canada. Area burn is highly episodic from year to year, ranging up to 7.6 million hectares. And you can see a decadal average in the bottom graph, and you can kind of see this quiet period and then ramping up. And we cooled down in the knots for a while, but I think this is only temporary, largely due to large-scale climate patterns. Lightning fires, depending on what time periods you look at, and what regions, about 35% of the total fires, but they represent 85% of the area burned. And fire size, a few large fires, 3%, are over 200 hectares, but they're responsible for 97% of the area burned. So the tail wags the dog. A few critical fire days, a few critical fires are responsible for most of the impact. We can talk about thousands of fires and millions of hectares, but it's really the impact that's important. So, and this just gives you a graphical image of how much fire there is in the landscape. And this is the 80s, 90s, and knots up to 2007. And it pretty well shows you where the boreal forest runs in Canada. There is less fire in eastern Ontario, but otherwise, that's a good map of the boreal forest. So, fire issues. We spend an average of $800 million a year on direct firefighting costs. These costs are rising. Brian Stocks has a lot more detail on those aspects. The United States spends billions of dollars on fire suppression. Of course, health and safety of Canadians, evacuations, smoke, property, timber losses. I mentioned Slave Lake. That was the second most costliest natural disaster. Kelowna was also in the top 10, I believe. And you know, these are significant events. Kelowna was $250, $300 million. Slave Lake was $700 million. So these are significant. But fire is a natural part of the forest, and so there's this aspect of trying to balance the positive and negative aspects. But what we do know is that traditional approaches to fire suppression, fire management, may be reaching their limit of economic and physical effectiveness. So we have to start thinking about new approaches. Now, the bottom graph there shows where fires were actioned in the red dots, and the kind of the purple or mauve are fires that were not actioned. And you can see the southern areas where the people are. Alberta and BC in recent years have had a fire suppression policy for just about every fire. So we often talk about impact in terms of the wildland-urban interface, and one of the things that we look at are evacuations. And this is work done by Jen Beverly and others, and there's about 100 people that are evacuated from 10 communities every year, but 20 communities and 70,000 people are threatened each year. And the reasons for these evacuations are the obvious ones: threat to human lives and properties. But smoke also plays a major role in evacuations. Transportation issues. Some of these are remote communities, and there's only one road into town. And if the fire threatens that road, you have to get out. And then there's some that are unknown. So this is how I view the world of fire. Okay? And by this, I mean looking at fire activity over a region, over a period of time. Individual fire, wind is very important, but I'm talking about you know, Western Ontario over a month or longer. These are the things that are important. Fuel, so how much fuel, how dry it is, how it's structured, what type of fuel, these are all important things. You need it to have a fire. Ignition, there's human caused, and there's lightning. Those are the two primary. And weather, and I may be biased, unabashedly biased, but I believe weather is the most important factor. You need those other two, but weather really drives a lot of this. Temperature, precipitation, atmospheric moisture, wind, sunshine, upper atmospheric conditions, and we'll talk a bit more about that. These are really critical. And the fourth factor is people. This isn't a natural factor, but as long as there's people in the landscape, we build roads, we build cities, we grow crops, agriculture, and this fragments the landscape. And of course, we try to manage fires as well. Now, weather, as I said, I believe it's very important of the three natural factors, but it's also involved in the fuel factor. One of the critical aspects of fuel is how dry it is, and that's a function of the weather. Lightning is also a function of the weather in terms of atmospheric stability and moisture. So what can we do? Well, we can't control the weather, so our options are to manage fuel and human-caused ignitions. And we can do prevention, education, restricted fire zones, reduce or eliminate industrial activity during periods of high fire danger, and we can enforce those rules. Fuel, and the United States has done a lot of work on this, and Canada's doing some as well. We modify the fuel, create fuel breaks, reduce fuel load, change type, at the landscape level or around communities, areas of high value. Also, we should be looking at using sprinklers more in Canada. It's part of the toolkit that I think we haven't used enough of. So some of the things that I talked about weather are short term, but some of them are longer term. And there's patterns in our climate that run anywhere from ENSO patterns, which run 2 to 7 years, to decadal patterns like Pacific decadal oscillation, Atlantic multi-decadal oscillation that runs out 50 years or more. Understanding these relationships are really key to help seasonal forecasts and even multi-year forecasts. So as I mentioned, ENSO, PDO, Pacific decadal oscillations, these influence the weather, which then influence fire activity. And we're just starting to get a handle on these things now. And there's recent publications out, and there'll be a lot more, but I expect big movement, more understanding of what's going on in our climate patterns in the coming decade. So I mentioned blocking ridges or stationary ridges, sometimes called omega blocks, and this is very active right now because this is part of our warm heat wave, record-breaking wave, is when you see a shape in the upper atmosphere of a Greek symbol omega. It's hard to see there, but the upper ridge. And what's happening in the upper ridge is that you have air that is descending. And as it descends, it's the opposite of the water cycle that you learned in grade 3. It warms and dries. If that sits there for 7 to 10 days, all your fuels dry out. And then if you have some ignition, then you've got fires. And when the upper ridge breaks down, you often have wind events. And this leads to significant area burned. In the future, it suggests that we'll see more blocking ridges of greater intensity than we see today. So let's talk about climate change projections. There's a whole bunch of models, over 20, general circulation models, global climate models, GCMs for short, and they suggest a warming of 1.4 to 5.8 degrees Celsius. And this is significant. If Toronto warmed by 5 degrees Celsius, it'd be like modern day Tennessee or something like that. So it's a significant warming. Greatest increases will be at high latitudes, over land, winter and spring, except for the Arctic Ocean, ice cover will be seasonal. So there will be big changes there. Projected increases in extreme weather. Now this is really important for fire because, as I said, there's just a few critical days that drive much of the fire activity. And individual fires, it's wind. In the future, we expect wind to become more extreme. The average may not change much, but we expect more extreme wind events, and that could cause real problems. The two maps there just show observations in the top, and it shows warming by decade, and Western Canada, Alaska, Siberia have been warming significantly. And this is a projection for 2050, and you can see patterns. And notice that not everywhere is warming. So when they say global warming, doesn't mean the whole warm will warm. There are ocean currents drive weather as well, and off Labrador there may be no change or actually cooling. And you can see that in observations as well, that there's been some cooling near Greenland during that period. So as I mentioned, variability is a real problem. Some places you see fire and then you see flood. Other places you see flood or a wet season and then fire. American Southwest, you need a wet season to create enough vegetation to burn in the following dry summer. Many parts of Australia is the same way. You need moisture before you get the flood. And as I mentioned, wind is a real wild card in this. So I was listening to CBC the other night. I'm a big fan of CBC radio, those who know me, but I was really mad because they were doing a show on climate change, and they said the temperature's been cooling the last 15 years. And I'm saying, what planet are you on? Okay, this is, there's a website, this is from NASA, and this is global temperature, and it goes back to about 1880. It shows uncertainty, which is getting less and less. But the 10 warmest years, 9 have been in this century. Only 1998 was in last century, and that was a very strong ENSO event, El Nino event. So we are warming, and we're continuing that trend. Last year was a La Nina year, which generally means cooling, but yet it was the ninth warmest year, despite it being. And if you remember, the forecast for our winter was going to be bitterly cold because of La Nina. And we've had one of our warmest winters on record, despite it being a La Nina, which is coming to an end. So I'm just going to show you a simulation. This is from the Canadian model, and it shows temperature by year over the globe. There's the temperature 2015, 2020, temperature scale on the bottom. And as you can see, much of the globe is getting much warmer. These are in degrees Celsius, and so much of the north is looking at 5 to 6 degrees Celsius warming. So let's talk about what may happen to area burned in Canada. And this is earlier work done a few years ago by myself and others. And it suggests maybe a doubling of area burned by the end of the century using 2 GCMs. And you know, a doubling, if we're 2 million hectares, that's 4 million hectares. It's really important as to where those 4 million hectares will burn. Once again, it's impact. So if it burns in the far north where there's no people, no big deal. If it burns Slave Lake, it is a big deal. Now there's been other work as well. This is by Mike Walsh and others. And so our estimates of doubling look conservative to this work, which suggests increase of 2.5 to 5.5 times for Western Canada and Alaska, using different GCM scenarios and looking at mid-centuries and late century. So, you know, they're suggesting significant increases by middle of the century, according to this work. Now, there was work done by Gillette, and, you know, is area burned related to temperature? And from this paper, it suggests there is. And then it goes on to ask, well, is this caused by human-caused warming? And they used a GCM and they turned off the natural variation and just had human cause. And from that work, it suggests that the increases we've seen in area burned in Canada are due to human-caused warming, okay? Now, some people still don't believe that the people are having an impact on our global climate, but the evidence is overwhelming that we are and have been and will continue to influence our climate. Now, we found in a lot of the work I presented that fire, area burned, fire occurrence is related to temperature. And you say, well, why temperature? I can understand wind, but why temperature? Well, there's 3 reasons for it. First, as the warmer you get, the more evapotranspiration you have, which means your fuels are drier, unless you get a significant increase in precipitation. For every degree of warming, you need about a 10% increase in precipitation. Most of the models show that most regions do not get that increase in precipitation. So fuels will be drier. When fuels are drier, fires are easier to start and spread. Second, the warmer it is, the more lightning you have. And the more lightning you have in Canada, the more fires we get. Third, the warmer it is, the longer the fire season. So, and there was a paper by Marc Prigent and others that looked at temperature and area burned for Canada at different scales. And, well, they looked at a number of variables, but temperature came out to be the strongest correlation. So more recently, we've looked at global DSR, which is daily severity rating, which is an indication of how much energy effort is required to suppress fires. And we've looked into the future using 3 different models, different scenarios, and this is just one of them. And if all the models agree, it's red. If they disagree, it's blue. And you see most of them agree that there's going to be significant increase in DSR, which means it's going to take a lot more effort to suppress fires in the future, according to this. And this is mid-century, this is late century, and we did the same thing with fire season length. And all the models agree that North America, most of Siberia, are going to increase, and most of these increases are 20 to 30 days in length. That's mid-century, end of century. There's not much change. Many parts of the globe near the equator have a full year fire season potentially already. So, you know, just try and summarize, what's our future going to look like in terms of fire activity? We expect more area burned, and much of what I'm saying applies to Russia, and I would argue United States as well. We're going to see more area burned, more fire occurrence, longer fire seasons. Fire intensity, there's suggestion that it's going to increase. Fire severity, depth of burn, there are indications it's going to increase as well. The maps on the right-hand side, work done by Mike Watton and others, looking at fire occurrence in Canada, and this is 2090 caused by lightning, and this is 2090 human-caused fires. And these are largely driven by fuel moisture. Lighting was not changed from present day activities, so these could be considered as conservative, at least in my view. So there's also a potential for positive feedbacks. As permafrost thaws, it releases greenhouse gases. Also, as peatlands, which hold a lot of carbon, as they become dry and burn, it could release more greenhouse gases, which causes more warming. So what's going on here is that we have greenhouse gases causing warming, causing fire, which then causes more greenhouse gas release, which causes more warming, and so on and so forth, until there's a vegetation feedback eventually. You start running out of fuel. So this is work done by Mike Watton and others, and just using a level of protection model, saying if we want to keep our current level of suppression effectiveness, given climate change, how much would we have to spend? Well, to maintain the current level of fire escapes, we have to double our suppression effort in terms of resources by 2040, using the scenarios that they used. So it's going to cost more money to have the same level of protection. So I'm painting a pretty bleak picture, and I don't want you to get me wrong. Not every year the whole country is going to be on fire. Some years it's going to be wet. Some years it's going to be floods. But on average, we're going to see more fire in the future. So what can we do about it? Well, health and safety of Canadians or Americans, Australians, that's a priority. And we can start addressing that through improved fire weather and fire behavior system. The Canadian Forest Fire Danger System is used across Canada and many parts of the world. It's a great system. It was developed 30 or 40 years ago and needs, the demands on fire management agencies, land managers have increased, and it needs to be updated, and that's ongoing right now. Adaptation options for fire management agencies, respect to climate change, altered fire regimes, community protection, adoption of the Canadian Wildland Fire Strategy. After Kelowna Fire in 2003, there was a Canadian Wildland Fire Strategy, which has largely has not been implemented yet. And there's a lot of good ideas in there. And there's a section on climate change as well. Protecting buildings, communities, fire smart programs. We're going to hear a lot more about that. In the United States, they're called FireWise programs. Reduce the risk to property and communities. Building materials, landscaping, defensible space. Spotting is a real problem, though. You can treat fuels around the community, but if you've got spot fires as far as 2 kilometers traveling, this is a real problem. Treating fuels near communities, changing fuel type, using sprinklers. There's more people living and working in the forest, so the risk is going to increase. We've got the Partners Protection website there, and we'll hear a lot more about that soon. So I'm going to summarize here, and fire and weather and climate are strongly linked. A warmer world will have more fire. Changes in forest fires may be the greatest early impact of climate change on forests. Increased risk in the future due to increased exposure, increased fire activity. The bottom line is there will be more impacts, there will be more incidents like Slave Lake and Kelowna in the future. Thank you.
Okay, so Mike's done a great job keeping us on schedule, and we've got time for questions. So questions of Mike? Brian first, and then Bob.
Mike,
sorry, do we need, can I apologize, do we need to use the microphone? We are recording this, if people don't mind, if you could use the microphone.
yeah, Mike, it's Brian. I just wanted to ask a question about the episodic nature of fire. I think, and we've talked about it before, but just like the highly episodic nature of fire from year to year in terms of area burn, numbers of fires and things like that, makes it really difficult to budget in terms of fire management programs. At the same time, it makes it difficult to look for a climate change signal when it comes to forest fire statistics. And it seems that even though we have some strong ideas in terms of what the future looks like, we haven't been able to make a strong case statistically for increasing fire activity. We haven't seen a climate change signal, I should say, in the record to date. And we know the reasons why that's difficult. But for the sake of policymakers, you'd think that we might need to be able to prove that. And I just wondered whether or not we're getting closer to being able to answer some of those questions.
Well, there's some statisticians in the audience that are probably very equipped to answer that question, like Doug Wolford over there. I would argue in part that we have shown that increases in fire are due to climate change in the Gillette et al. Paper in 2004. So I would say that you're right in that, you know, we really need to show statistically, you know, peer-reviewed research that, you know, this is real and it's happening. And the problem, as you pointed out, is due to the highly episodic nature of fire. Year to year is almost independent in terms of fire numbers and area burned. But there is some work it does suggest that this is due to human-caused climate change. And,
yeah, Mark, sorry, I've got Bob first. Sorry.
Sorry, I'll give you the mic in a minute. Bob Dorn, I'm just wondering, and you may not be the correct person to ask this question of, but and so Slave Lake kind of brought this to mind, and that is there a change in terms of the approach to establishing perhaps different protocols or looking at fire behavior from the sense of when do you go at it and how hard do you go at it to prevent things like Slave Lake? And I'm not saying that it could have happened, that it could have been prevented, but I'm just wondering if there's a move in that direction, because I'm not really familiar with the protocols with regard to fighting wildfire.
I'm not sure how much Peter's going to address that. Simply, areas under protection, initial attack is a priority. You hit it hard, you hit it fast when it's small, okay? When the fire is the size of this podium, you can get it under control. If it's the size of this room, it's starting to become a problem under severe conditions. So initial attack, initial attack, initial attack. But I think Peter's going to talk more about the actual strategy of fire management. A little bit, all right.
Yes, Mark Baker. I've heard suggested by some people that the actual fire suppression itself can be causing issues because you're not letting it burn naturally. You're getting a buildup of duff in the forest itself. So eventually it just gets to the point that it burns, and then it burns completely out of control, and you can't stop it. How does this sort of dovetail into the model you've been discussing? Okay,
that is a good point. In much of the boreal, we don't have to worry about things like that because it really hasn't changed its nature to a large extent. But in parts of western United States, BC, and what I call the Front Range or East Slopes of Alberta, because fire suppression has been so successful, the fuel has changed from an open forest landscape to a closed canopy. So when fire does occur, it's much more severe than it would otherwise be. So yes, in part, we are victims of our own success in terms of that, and also in terms of expectations of people. They think that fire management agencies can put out all the fires all the time, and that's just not the case, okay? Their expectations are too high. But your point is well taken that in some ecosystems, because we have suppressed fire, now we have a bigger problem. And much of western United States is in that boat.
It's time for another question. I haven't seen a hand go up. Is there a last question before that mic go? Did I try a question of you just as we wrap up with Mike's session here? Mike shared with you some of the evidence that he's been leading on the research of, others are part of looking at. Just a sense in the room, are you expecting more fire? If I look at 25 years or so, did you hear enough of evidence here? Or are you looking for more research to understand the risk? How many people think there'll be more fire in the next 25 years or so? A lot of hands up. And those still looking for more research, more information, who are not sure there'll be more fire? I don't see any hands up right now. So Mike, you really convinced this audience. Bob, you got a question?
I just wonder if it's not not necessarily more fire. I mean, I believe that there easily could be.
However, it may be an issue of where those fires occur, and I think that that's the big concern in our minds.
Yeah, and I think what Mike was sharing, based on his research, but also research by people like Mike Watton, who's here today, and others, to have the same level of protection that maybe the insurance industry has expected in the last 40 or 50 years will be harder. I mean, Peter will talk about this in a moment, some of the things that can be done. You could have more fires start, but you can put them out if you get there quickly with lots of people and spend lots of money. Can you please join me in thanking Mike for